Okay. Can you guys see my screen? I started sharing it. Yes. Okay. Thank you. Okay. Let me know if you can't see it. Okay. So. So very simple. I don't need to tell you about introduction and all those things because in our life, D2A and A2D has become uh, super important, right? So this is a simple digital to analog converter. Okay. So let's say this is B0, B1, B2, and so on, Bn, whatever. Doesn't matter which number is it. Output is V0. Okay. This is digital to analog. Right. The other one is analog to digital. V in. Then you have B0, B1, B2, B3, B4, B5, and so on, like this. Right. Now, first thing is, how do you apply the inputs here? You know this V in and all. You have some voltage source or some voltage across the resistor can be an input. But how to give these inputs? Okay, this you use switches, right? Simple. Yeah, not visible. Okay, let me present it again. Is this visible now? Okay, fine. So where your binary inputs can have the options 1 or 0, so switch. Okay. Now this we can discuss. First we'll discuss about D2A, then we'll discuss about A to D. So there is a reason why to do that. That will be very clear once we discuss this, right? So you might have seen many followed by I have a lot of problems for you guys. Okay, see this. There are some problems somebody asked, so I thought of doing it here. There is something called weighted RDAC, right? So before going into this, generally when a binary number is given like this, let's say B3, B2, B1, B0, base 2. If at all you want to convert it to decimal, okay, forget about this for some time right now. What will you do? We know already, right? B0, 2 power 0, plus B1, 2 power 1, plus B2, 2 power 2, plus B3, 2 power 3. If you know this conversion, right, you are already into analog domain, right? So whatever the logic that you're talking about, okay, so finally you have to get this. That's it. You have the inputs B3, B2, B1, B0, and you get these multiplication factors 2 power 1, 2 power 2, 2 power 3, and so on, right? So, keeping that in mind, mm, all of you might already know about the op amp, right? So, let's say, for example, I have an op amp minus plus, right? So, this is inverting op amp, right? So, let's say this is V0 output, let's say this is RF. Now, just understand this point. I will take only 3 digits B2, B1, B0. That's it. Okay. So I will have a resistor R. Then I'll have some resistor 2R. Then I have some resistor 4R. Something like that. Now what about the inputs? Where to give the inputs? I told you inputs is given through a switch, right? So this is, let's say, B2, B1, right? Okay, let me write it clearly. Now, I just want to give you some little emphasis here, okay? So let's say if B2 is 1, for example, that means that this is connected to plus 5 volt or plus V reference. If it is 0 means that is connected to the ground. Let's assume there are only 2 voltages that are possible, right? So your switch has to have a feasibility to move, correct? So this is the switch I am connecting like this, B0, B1, B2. Now there is plus V reference here. So a switch, right, can connect to plus V reference or minus V reference depending on which value you are applying. And also the another point is here. So you can also have one more input, right? This is connected to ground, right? So this is very clear and evident. Okay. So why I took MSB here is very simple. For example, right? I will take the same circuit and I'll do some kind of modification. Let's say, for example, B2 is 1, B1 is 0, then B0 is 0. Let's say for this combination, how the circuit will look like, right? Okay. You guys can still see the screen or no? You lost it. Okay. Can you see it now? Okay, better I will share the entire screen. Okay, can you guys see the screen now? Okay, all right. So these are the things which you know, but for the people who don't know a little bit about it, I'm just highlighting the fact. Minus plus, this is ground 0. Then you have R. Now since B2 is 1, B0 is 0. I mean B1 is 0, B0 is 0. So that means that this is connected to plus V reference. Then this is 2R. This is 0. That means that this is connected to ground. That is 0 volt. Then this is 4R. This is also connected to 0 volt. Right? This is connected to 0 volt. This is plus V reference. And there is V naught. This is RF. Correct. Now you look at it. See, now this is in negative feedback mode, right? The op amp is in negative feedback. That means that virtual short concept applicable. Hmm? That means that whatever you see here, right? Whatever the voltage that you see here, you see the same voltage here, right? Now you look at this. This node is at 0 volt, right? So this is 0, this is 0, there is no current. There is no current that flows through. This is 0, this is 0, there is no current flows through. Only current flow from here, right? So, and if I simplify it, and you already know this, right? What is this voltage? What is the relation between V0 and V reference? You can say like this. Okay, this is 0. The current entering the terminal is 0. So whatever is the current that is entering in, the current has to leave, right? So at this point, if I apply KCL at point A, so V reference minus 0 volt divided by R is equal to 0 minus V naught by RF. So V naught is minus V reference into Rf by R. Otherwise, V naught is minus V reference, sorry, hmm, that implies V naught is minus Rf by R into V reference. Now what we can do, we will take it a bit. This if I apply negative V reference, let's say, what will happen? Your V naught will become what? Plus Rf by R into V reference. This is all happened because B2 is 1, right? So there is a multiplication factor of B2. Are you getting it? Right? If B2 is 1, then this will be valid. Right? Mind you, mind this here, it is minus V reference I am applying. Right? Similarly, if I write for individual B2, whatever we saw right here, B2, B1, B0. So what you will get? We already know that, right? So V0 is V Rf by R into B2 into V reference plus Rf by 2R into B1 into V reference plus Rf by 4R B0 into V reference. Right? Are you getting it? Now if I put everything together, V0 is in the denominator. If I look at it, there is 4R common and there is Rf also come out, correct? So 4R, right? This is 4 times B2 plus 2 times B1 plus 1 time B0 into V reference, right? This, you neglect this V reference and other thing, okay? This is like a scaling factor, right? This thing. So V naught is some scaling factor K into 4 times B2 plus 2 times B1 plus 1 time B naught. That's it. Now, your inputs to this system is what? B2, B1, B0. What is your output? V0. Right? And there is a scaling factor K. We will come to that. What is that exactly? Uh, guys, are you clear with this? Yes or no? Let me know through your chat box. Is this clear? Okay. So now we will come to the fundamental parameters we have to consider for designing a ADC or DAC, right? So if you look at this, this factor is 4 times B2, 2 times B1 plus B0 into, you look at this factor, K is RF into V reference by 4R, right? RF into V reference divided by 4R. For example, if I take R equal to RF, just consider that what will happen, these two gets cancels out. V0 is 4 times B2, 2 times B1, 1 time B0 into V reference divided by 4. Okay. So for every DAC, we have to have some parameters, right? There are some parameters that are characteristics that you can quantify. So the first characteristic is resolution. Right? So You keep hearing this term resolution many times, like your camera, that, this. How good is it? How fine is it? Right? So what is the resolution? How to define the resolution of a DAC? Right? The output, very simple. Okay, which pen I can use? Ah, this one. The change in the output when there is one LSB. This is very important. Change in the input. That's it. The change in the output voltage when there is one LSB change in the input. Right. So now you look at it for let's say for example this is B2, B1, B0. Right. You have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, double 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. So I'm messing it up a bit here. So pardon me. Hmm? I don't want, actually I want this to be in a clean line. Okay? I'll write this here again. The change in the output voltage when there is one LSB change in the input. Input is binary, right now. So you cannot say voltage or whatever it is, right? One LSB change. What is this one LSB change? We'll see. We have B2, B1, B0. Accordingly, you have V0, right? So, and you know the governing equation. So you have 0, 0, 0, 0, 0, 1 possible combinations of B2, B1, B0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, correct? 8 combinations. Now, 0, 0, 0 means what? You, so this is, if you put B2, B1, B0, 0, 0, then output will become 0 because all are zeros. Now, if you make it 1, then what will happen? V0 is nothing but V reference by 4. Now, you see this. What is the change here in the input? One LSB change. So, what is this change is called as V resolution. So, for this device or for this DAC, V resolution is V reference divided by 4. All right. Then 0, 1, 0, if you put it in this is 1, this is 0, this is 0, right? 2 into V reference by 4. This one, 3 into V reference by 4. This is V reference. This is 5 times V reference by 4. This is 6 times V reference by 4. This is 7 times V reference by 4. Now, if you look at this is also one LSB change, right? So, obviously, what is this called as? What is the change in the output? This is also V resolution. V resolution is 2 times V reference by 4 minus V reference by 4. Again, this is 1 LSB. That means what? What is this also? V resolution. Again, this is V resolution. Again, this is V resolution. Again, this is V resolution. Again, the change here is V resolution. Are you getting it? So, if I sum all the V resolutions, how many? 1, 2, 3, 4, 5, 6, 7. 7 times V resolution is equal to 7 times V reference by 4. Simple. So, V reference by 4. So, again you got V resolution is V reference by 4. Now, what is other parameter? Right? That is VFS. What is full scale voltage? This everyone knows, right? Simple definition. So what is the output when input is all the inputs are 1 1 1? Here we know already, right? So the output that is corresponding to this is nothing but VFS. So according to this, V full scale is nothing but 7 times V resolution. I mean 7 times V reference. 7 times V reference by 4. That means that I can write, since V reference by 4 is V resolution, right? So 7 times V RES. Or I can also say VRES is VFS by 7. Clear? So what happens right now here is V resolution and full scale voltage I can correlate. Since this is 3-bit DAC, I got 7 in the denominator. Right? That means that I can write this as VFS divided by 2 power 3 minus 1. If it is n-bit DAC, then V resolution is nothing but VFS divided by 2 power n minus 1. Okay. Are you guys clear? Let me know through your chat box. That's all. That's the discussion of the first one. Hey, are you guys clear? Say yes or no through your chat box. Hmm. Okay, Hari Prasad, did you understand? Okay, all right. Okay, Kushbu, then why you are not typing? Okay, all right. Now, if you look at it, see, for example, uh, if I take RF is equal to, let's say, 100 kilo ohm, because you also want to have more gain and all, right? And if I take R equal to R, this is 100 and this is 200 kilo and this is 400 kilo. First issue is, can we get exactly 100k, 200k, 400k resistors like that? Exactly multiples of 2. You might have seen 1.5 kilo ohm. That means 1.47 kilo ohm is available. You may not get 3 kilo ohm. You may get something else. You may not get 4.5 kilo ohm. You may get something else, 4.7 kilo ohm. So getting these numbers exactly is very, very challenging. 100, 200 and all. And also, this is 3 bit, so it's fine because you are stopping at 400. What if you have 16 bit? You see this resistor, right? This is MSB resistor. The MSB resistor is R. By now you understood why it is called MSB, because this has more weight. You look at this equation, right? If B2 becomes 1, right, then V0 will be V reference. If B0 becomes 0, then I mean B0 becomes 1, only this is V0 is V reference by 4. By now you already know why it is MSB. So MSB resistor is R, then your LSB resistor is what? Like if it is R, 2R, 4R, like this is 4R, right? 2 power 3 minus 1, correct? So your LSB resistor is 2 power n minus 1 into R. If it is 16 bit, it is 2 power 15 into whatever is 100, which is a very big value, very big number. Are you getting it? Right? And what happens is, what is there in that? If it is very big, let it be big, right? What is the problem in that? So the problem is this, okay? You have to have larger area, right? I mean, larger length. It also comes up with the space constraints, right? That's one. So that's the second issue. That is issue number one. This is issue number two. Issue number three is tolerances, right? So this plus or minus delta, okay, create a lot of mess. So it will make sure that, you know, since these are not ideal values, the resistance values keep changing according to the time, temperature, and other parameters. So it would be extremely difficult to maintain. Uh, you know, uh, it is what I mean by extremely difficult to maintain. Maintain the consistency of the V naught corresponding to say. So let's say you give 100 today, you may get 2 volt. Tomorrow, if you apply 100, same input, you may get 2.2 volt. Day after tomorrow, 1.9 volt. So which is not consistent at all because the tolerances are huge, right? So that is the reason why we go for. There is one more DAC. This is R2R DAC. So the name itself says that, right? So let's say you have this op amp again connected in the similar way. Then you have a resistor V0, right? So just a minute, just a minute. Hello. Okay, guys, I'm back. I got a call, so I need to take it. Okay, can you guys see my screen yet? Still? Yeah. So let's say this is RF, right? Then this is R. So you don't need to by heart this, okay? So you can analyze. You just need to know how to analyze this, right? So there is R, 2R, no? This is R, this is 2R, again this is R, this is 2R. For the simplicity, I am just, you know, considering only 3-bit DACs, right? Now again, you have V reference that is coming up. Again, the configuration is same. This is minus V reference that you have. Then this is, let's say, let's decide that later on. Okay, let's say this is okay V0, V1, right, and V2, and you have something called ground 0, right? Now, okay, what is RF here? That's a big question people might be thinking, right? So you might have heard of Thevenin's theorem. Where is this? Okay, fine. You might have heard of Thevenin's theorem, right? So when you connect, when you think B2 is B1, no voltage is applied. It's zero. It's not 0 volt. This is zero. That means your network effectively. Okay, I will answer most of the questions here. Why I considered extra and all. This is 2R. This is R. This is 2R. This is R. You see, this is R2R, 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 right? R2R. Finally, there is R2R here extra, right? Now these are at ground, right? 0, 0, and 0. This is 2R. Now you look at it. What is the effective resistance here? 2R and R. So if I look at that in that way, the effective resistance is R, right? Because they are in parallel. Both the nodes are the same potential, right? This is R. Now you see, this and this is in series. So what will happen? Just a minute, guys. Yeah, I'll call you back. I'll call you back. I'll call you back. So this is again 2R, right? Now what is happening? 2R, 2R, parallel. So you will get R. R, R, 2R. This 2R and this 2R is again R, right? Effectively, what is that? The entire network when B2, B1, B0 is 0 is giving is this R. So from this node, you look at this. See, right? This entire left to the left of that is all R. Then there is R here minus plus, right? There is something going here like this RF, right? So the effective resistance seen from here to here is again this is 2R. So if you don't want extra additional gain, you can just maintain RF is equal to 2R. You understood? So one can design in that way. So you can maintain this as a 2R. Okay, are you guys clear with this point? Please let me know through your chat box. Am I too fast or am I confusing you guys? Or is it clear? Let me know through your chat box, please. If you don't let it know, then I have to call out randomly the names and then I'll ask. Okay, fine. Okay, Bunty is asking, can you explain it again? Okay, what is that you're asking, Bunty? Which part? Oh, how the 2R is decided. Okay. See, you know this, right? Non-inverting amplifier or inverting amplifier you might have. You know about non-inverting inverting configurations? Right. So let's say, for example, this is RI. Hmm? Let's say this is RF. Hmm? This is Vin. So we know that V naught by Vin is what? Minus RF by Ri. Right? Let's say I don't want to gain. That means what? V naught is Vn. Let's say, for example, magnitude of V naught is magnitude of Vn. That means what? RF, I can choose it as Ri. So the effective impedance seen from this node should be equal to the effective impedance seen from here. From this node to towards V naught. Are you clear? Right? Now look at it. These two are in parallel. Let's say if all the see when you apply Thevenin's theorem to find effective impedance or effective resistance, right? You should not apply any voltage at the input side. V2, V1, V0 should be 0. So when you make V2, V0 they are all 0, everything gets connected to the ground. So this 2R and 2R will be parallel, so it will become R. Then that will be in series with this, that will become 2R. Then again, okay, what I am saying is this. These two are in parallel, so you will get R. 2R and 2R parallel, right? The effective resistance is R. Then R and R in series. Then effective resistance is 2R. Then again 2R, 2R in parallel. R, 2R, R, again 2R. So effectively, the potential seen from this to the left, right? So let me escape from there, right? Effectively, the potential seen from here is 2R. So since I don't want any gain from the op amp, I can just choose 2R as a feedback resistor. That's how the design is done. If you want more gain, you can choose something else. That is not mandatory. So now let's see why I call this as MSB. That's very straightforward, right? Again, let's assume B1, B2 is 1, B1 is 0, B0 is 0. What will happen? You have this resistor here. This is 2R. This is connected to minus V reference. And you already know by now why it is called as minus, why I have taken this as minus V reference, right? Because this is an inverting amplifier, right? 2R, this is R, this is 2R, right? And this is connected to 0, this is connected to 0, this is again connected to 0. Okay, this is 2R. Now 2R, 2R in parallel. So you will get R. R and R in series. You will get 2R. 2R and 2R in parallel. Again R. R and R in series. Again 2R. So effectively what are you going to get is this. Let me erase this right part. The effective or equivalent circuit I'm drawing now. There is R here. There is 2R. This is connected to minus V reference. And this goes to 2R. One can quickly do that. Okay, this is 0, 0, 0 means what? 0, 0 means 2R, 2R, R. R and R series 2R. 2R, 2R in parallel. Again R. And again R and R in series will get 2R. That's it. Here. Then here it is 2R. Can somebody quickly calculate and tell me what is this value? V naught. This is in negative feedback mode. So this is 0. Correct? So this is Vx, for example. Right? So what we need to do, this is again 0. I can assume the current is flowing like this. Current is flowing like this. Current is flowing like this. So at the node Vx, input current is 0 minus Vx by 2R plus minus V reference minus Vx by 2R is equal to Vx by R. Right? So you can easily find what is Vx. This is minus Vx by 2 and this is minus Vx by 2 minus Vx by 2. So you will get minus Vx. is equal to, right, minus Vx minus, okay, calculate and tell me what is that. Hmm. Minus Vx by 2 minus V reference by 2 minus Vx by 2 is equal to Vx. So what is this minus Vx and minus Vx by 2 is minus Vx minus V reference by 2 is equal to Vx. So if it goes this side, 2 times Vx is equal to minus V reference by 2. So what is Vx minus V reference by 4? Now you know the Vx, right? Now you can apply KCL here. Incoming current is equal to outgoing current. This current is assuming 0. So Vx minus 0 by R is equal to 0 minus V naught by 2R. So what is V naught? Minus 2 times Vx, and we already know minus 2 times minus V reference. Vx is minus V reference by 4. Just now we got, right? Minus minus 2. So V naught is V reference by 2. This is for what? This is when B2 is 1, B1 is 0, B0 is 0. Similarly, one can do B2 is 0, B1 is 0, and B0 is 1, and find out V0. Okay, hopefully they may get a V reference by 4 eyes somewhere. Okay, so from that you can say that, since B2 is making V0 very high, so it can act as MSB, and B1 is B0 is making V0 low when compared to this, so you can make B0 as LSB, something like that. Okay, that intuitive understanding should be there, right? So please check it out. This value, whatever it is, don't look for exact value. I am not sure. I have to calculate and then see. Are you guys clear with this? Okay. So now, if you are very clear, then very good. This is a most popular DAC. Now, what are the issues in this? There are no issues. Well, first of all, when I say there are no issues, there are issues actually. So you just need two types of resistors. Very good advantage, right? You just need R and you just need 2R. With that, you can build the entire circuit. Not only 3-bit, you can have 4-bit, 10-bit, 15-bit, 16-bit, 18-bit. Everything is going to be the same. It is just a R2R network you have to keep adding. See this? This network is there, right? R2R network. You just keep adding it. R2R, R2R, everywhere. Okay. And the biggest issue here is this. Okay. RS. The biggest issue is it may tend to be non-linear. Why? Because non-linearity will be more. Okay, of course, R2R ladders are there. That's great. But what about non-linear? What do I mean by non-linearity is the question, right? So what I mean by that is this. Suppose if B2, B1, B0. Okay, intuitively think, okay? If B2 is 1, B1 is 0, B0 is 0, you calculate what are the resistor currents that are flowing through. I1, I2, I3, I4, I5, I6, I7. Okay, this is not iPhone I'm talking about. Okay, these are the currents, let's say, and there is IF. Now, I1, I2, I3, I4, I5, I6, I7. These are the currents flowing through different resistors. Suppose if B2 is 0, B1 is 0, B0 is 0, or B0 is 1, This I1, I2, I3, I4, I5, I6, I7, they are not going to be the same. The current magnitudes will change. If the current magnitudes changes, then the heat dissipation across the resistor changes. If the heat dissipation across the changes, then obviously we are making it more non-linear. Correct? Because your heat dissipation also responsible for the change in the resistance. R equal to R into 1 plus delta. The tolerance will come into picture. So not very much reliable. Okay. Not 100% we cannot rely on. These are like not closer to the reality, or not closer to, let's say for example, you are expecting in this case, all right, V naught is, let's say for example, V reference by 4 or V reference by 2. Let's say this value amounts to 2.5 volt, right? Uh, it may be 2.4 volt. For this, you may expect 1.25 volt. You may get 1.05 volt. Here, if you look at the difference, right, this is 0.1 volt. Here, if you look at the difference, this is 0.2 volt. If the difference is going to be the same, then I can have it an offset, okay, something like this, right? Your input, output, if I plot, right? So everywhere, let's say there is some offset here, right? When compared to the ideal, let's say this is ideal, okay, this is practical. If there is an offset everywhere, same offset everywhere, that's fine. But if in practical, it is not going to be like that. In practical, this is going to be like this, or like that, or like this, or like that, right? This offset is keep changing. So that's the problem. Are getting it? So that's the main issue with the R to R ladder. So what people have done is they have moved to something called as inverted R to R ladder. Right. So inverted R to R ladder, we will try to maintain the currents across all the resistors as same. So again, you no need to by heart any circuit, just you need to know how to analyze the circuit. Because in the exam, most of the time it's about the analysis. It's not about how much you remember about the circuit. Right? So what happens here is this. This is minus V reference, and by now you are very clear. This is 2R. Same R. R to R network is the same. Again R. Again 2R. Now again 2R. This you are already familiar, right? So instead of drawing from the right to left, I am drawing from left to right. Right. So now there is some feedback resistor here. By now you know already this feedback resistor what it should be. Correct. So 2R 2R R. R R 2R. 2R 2R again R. R R 2R 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 R. So this is also R. Right. So that the gain is going to be 0. Now you have this voltage, right? See this. The other terminal is connected to 0 volt. I'll extend it a bit. Right. Now this is a switch, right? This is a switch. Now what you do is, right, if you want to make this as 1, you connect to this side, the terminal that goes to the inverting. If not, you connect it to the ground. You connect it to non-inverting terminal. Here, this becomes the MSP, this becomes the LSP. One can easily calculate, don't need to worry about it. You see, right, if you connect this to here, right, Now you just look at this circuit, okay? Just this network. What I mean to say is, this is 2R, this is R, this is 2R, this is R, this is 2R, and this is 2R. Now I'm assuming that all these bits are 0. All the bits are 0. That means they are connected to 0. Now we look at this. This is minus V reference, right? Now this effective resistance is R, 2R, R, 2R, right? That means that this is minus V reference. This is 2R. This is going to be 2R. That means if there is a current I that is coming, it equally divides. This is I by 2. This is I by 2. So what is the current? I is minus V reference by R. So total resistance is, effective resistance 2R, 2R in parallel is nothing but R. The total current is R. If you look at the individual current, this is I by 2. This is I by 2. This is I by 4. Correct? Same thing. This is I by 4. This is I by 8. This is going to be I. So the currents are always constant across all resistors. What you are trying to do is, you're just trying to steer the current. That's it. So what are you trying to do? You try to steer the current. What is V0 now? Right? If this current comes, let's say, this is I by 8. This is I by 4. This is I by 2. Here, all the currents will sum up, right? So the total current is I by 2, I by 4, I by 8 multiplied by R, correct? This is minus. So the current is coming like this. This is I total. So V0 is I total. I total is this. And we already know what is I. Minus V reference by R. Correct? So V0 is, if I put a V reference by R here, so this is V reference by 2R. Minus minus goes. V reference by 4R plus V reference by 8R into R. R, R, R. Now, how to decide which is MSB and which is LSB? See the current weight. This is I by 8. This is I by 2. So the current that passes through this node is very heavy. Okay, this is I by 2. Correct? That's why it will become MSB. So I can put MSB bit here. Then this will be this. So V0 effectively is, right? So V2 by 2 plus V1 by 4 plus V0 by 8 into V reference. Correct? That implies if I solve it, this is V reference by 8 into 4 times B2, 2 times B1 plus 1 time B0. That's it. You just take any combination of B2, B1, B0. Are you getting it? Either you connect it to the inverting terminal so that the current will go to the output. Otherwise, you will convert it to, you will give it to non-inverting terminal. Are you getting it? So here the clue point is whether you give it to inverting terminal. Look at it. Whether you give to inverting terminal or non-inverting terminal, since it is a negative feedback, it is a short. Since these voltages are maintained irrespective of any switch position, right? That's where the current is going to be constant. So this is one of the most famous circuit of DACs. Those are R2R inverted. This is called as inverted R2R DAC. What is this called as? Inverted R2R DAC. Very simple. No complications at all. Whether you connect the switch to the inverting terminal or whether you connect the switch to non-inverting terminal, you eventually you are at the same potential. That's the reason the currents are always same. What you try to do is just steer the current. That's it. Okay, these are also called steering DACs. Steering DACs, right? Steering. You either steer the current to the output or steer the current to the ground. Okay. So those are the typical three types of DACs, and we are running out of time right now. I think it's already 7:58. We can take up a few problems. I think maybe we can start in the next session. I think we can solve these problems and then come back. We'll discuss about these problems, and then we also discuss about ADCs, which are very very important. And this is about the typical R2R configuration thing. The first one. This is the similar concept. Once we are clear about DACs, we know this. And this is inverted R2R ladder problem, right? This is R2R. This is inverted R2R. Okay. So we'll do it in the next session. Probably next session is going to be a 2 hour session. Are you guys okay with that? Because we missed some two classes, so I want to compensate. Next week we'll do a lot of problems on DACs, ADCs, and all, and also apart from that, we'll also discuss about